The last part of Module 5 is looking at Le Chatelier's principle. And Le Chatelier's principle basically describes how an equilibrium responds. In this case, shifting, left or, right towards starting materials or towards products. So it's how it responds when basically conditions of the reaction are altered. And so basically we have a number of stresses. I know we're all used to stress at this point in our lives, right? So we all deal with stress in different ways. And equilibrium reactions deal with stress in different ways as well. And so, when a stress is applied, to an equilibrium reaction, the reaction will respond response probably allow we respond to stress. We try to alleviate the stress. We try to get rid of the stress. And so that's what the equilibrium reaction tries to do as well. And so there are a number of stresses that we can apply. We have the notion of temperature as an example. We can think of pressure. Which is kind of hand in hand with volume. And then as well, we can think about concentration. So those are the stresses that we have. And so let's kind of just walk through each one of these. Let's start with the pressure volume stress. So basically, if we think about, we can say that an increase in pressure and realize that that is the same as a decrease in volume, right? An increase in pressure will cause an equilibrium reaction to shift to the side with less moles of gas. So that's the first kind of stress, as we could say, is, well, an increase in pressure. We can increase the pressure, or decrease the volume. That's resulting in the same thing. That'll cause a reaction to basically shift to the side with less moles of gas. You know, a way to think about it is, you know, that there is an equilibrium pressure. You know, pressure total. Increasing the pressure causes the reaction to reduce the pressure. Remember, this is the idea of removing the stress of the pressure that we just added, right? We just increased the pressure. So increasing the pressure causes that reaction to reduce the pressure back to the equilibrium pressure. And, you know, less moles of gas equals less pressure. So that's the stress of pressure, right? The equilibrium reaction has, you know, an equilibrium pressure. That's the total pressure of all the gases within the equilibrium. And if we're now putting a stress on that equilibrium pressure by, in this case, increasing it, well, then that reaction responds to that stress by trying to reduce the pressure. And since moles of gas and pressure of gas are directly related to one another, lowering the pressure means going to the side with less moles of gas. We then have the opposite being true for a decrease in pressure. And then we have the opposite in a decrease in pressure. And that would be the same as an increase in volume causes the reaction or the equilibrium reaction to shift to the side with now more moles of gas. And so we have the flip side of that coin, where we have a decrease in pressure or increase in volume. And so it's the same idea that, you know, the pressure decrease from that, or from the equilibrium pressure, causes the reaction to try and increase the pressure back to the equilibrium. And so again, there's that more moles of gas would then be, greater pressure as a result. So that's kind of our pressure volume stress. And so as an example of that, we could look at the reaction of 2 sulfur dioxides plus oxygen gas produces sulfite. So here we have a reaction, and then we could apply a stress. Say, you know, if the pressure was increased, which way would the reaction shift, right, to respond to the stress? So if we have our increase in pressure, we want to shift to side with less moles of gas. And so if we look at our stoichiometry, we would see that that would be, then the reaction would shift to products, or to the right. You could also say the volume was increased. Since the volume was increased, that's the same as the pressure being decreased. So that means we're going to shift to the side with now more moles of gas. And so that means we are going to now shift to the starting material side, or the left, because we have more moles. We have 3 moles on that starting material side versus 2 moles on the product side. And so we have to keep in mind that this type of pressure volume stress only works on equilibrium reactions that contain gases. So keep that in mind, right? This is not something, if everything was in solution, everything was aqueous, then that would have no effect as far as pressure or volume changing in terms of an equilibrium process. So the next stress that we could look at would be concentration. And so basically, with concentration changes, if you are increasing concentration, the equilibrium reaction shifts to the opposite side. If you are decreasing concentration, then you have the opposite. To the same side. So there's our idea. Increasing concentration shifts to the opposite side. Decreasing concentration, right, equilibrium shifts to the same side. So, and that's almost just like a Q idea, right? That if we increase the concentration of something, we're messing around with K, and now we're technically at Q. And so that means if we're increasing, a starting material, well, that means we would increase the denominator, and the reaction will respond by trying to increase the product side or the numerator, or vice versa. If we remove something, it's the same idea. It's just now the reaction tries to replenish that material that we're trying to remove. So we could break it down in terms of, simple addition. So if we add, starting material, equilibrium shifts, right towards the product. If we decided to add product, well, then the equilibrium shifts, left or towards our starting material. If we remove starting material, now the equilibrium shifts left, same side, making more of that starting material. And then if we remove product, it's going to shift to the product side. So that's the nature of addition or removal of material. So as an example of this, we could look at a reaction of solid silver nitrate going into H2O to produce silver +1 and nitrate -1. So here's an equilibrium reaction. And so I could add a couple of things here. Like, for instance, if I added, for instance, nitric acid is added to the reaction. So what is nitric acid? Well, nitric acid is much like silver nitrate, is going to dissociate into solution when we add it. And so we find that this is like adding product, because we see we have our nitrate as a product of this equilibrium reaction. So if nitric acid is added to the reaction is going to shift left or towards our starting material, because we're adding product to that particular equilibrium process. What if I say sodium chloride is added to the reaction? Well, what will sodium chloride do? Sodium chloride would dissociate as well to Na+1 and Cl-1. And so it doesn't look like that's increasing anything, because none of those match the materials above. But we might remember precipitation reactions, right? That silver +1 plus chloride -1 produces solid silver chloride. So this is like we are now removing starting material. And so that's why this is going to cause the reaction to shift to the right or towards product. So we have that, idea of, adding, apologize, we're removing product down there. that if we're adding material, we're shifting to the opposite side. If we're removing a material, we're shifting to that same side. And so here's a way to see that in terms of removal of silver via an old school precipitation reaction, or the addition of a material such as nitrate. What if I said, 500 milliliters of H2O is added to the reaction? What's going to happen then? Well, water is a pure liquid. Water isn't part of the equilibrium constant to begin with, so there would be, no effect, or it would remain unchanged. So there's some different ways of adding things, removing things, but also remember that we can add things and not have an actual effect, like we see here with this particular water addition. The last piece is looking at temperature changes. For temperature changes, we have to be concerned with the delta H of the reaction. And we want to treat delta H of the reaction as a starting material or product. If if our delta H is positive, so we're talking about an endothermic process, we would treat it as a starting material, meaning that this reaction needs heat to go forward, so we'll treat it as a starting material. If delta H of that reaction is negative, so now we're talking about an exothermic reaction, we would then treat it as a product. Thus, temperature increase is like an increase in concentration of delta H. So we have a shift to the opposite side, while then a temperature decrease, right now going the other way, is like a decrease in that concentration of delta H. And so now we shift to the same side. So that's how I like to treat delta H, is treat it as a starting material or product, right? If we're talking about something that's endothermic, we treat it like a starting material. If it's exothermic, we treat it like a product, right? And so then we have, these ideas of temperature increase is an increase in concentration, while a temperature decrease would then be a decrease in concentration of that idea of delta H. And then we have the shifts that correspond to those processes. So if you had, for instance, an endothermic reaction of, just say, A going to B, and our delta H is equal to something that's positive, we would write this like this now. The equilibrium now including that delta H on a starting material side. So an increase in temp would then cause a shift to product because we're increasing the concentration of that delta H, while a decrease in temp now causes the other direction. We would shift to our starting material side. If we had an exothermic reaction, right, it's still the same idea, except now our delta H is something negative. We would just then write that delta H on the product side, but we would still have the same responses that we had for the increase or decrease. So if we increase our temp, now we're increasing the concentration of a product, so we're going to shift to the opposite side or shift to the starting material, while if we decrease our temperature, now that's a decrease in concentration of a product, so we shift to that product side. So that's the nature of temperature and how that affects our equilibrium process. So as an example, we could go back to our sulfur dioxide example. So here our delta H is 50 kilojoules per mole. And so right away I would write that delta H in for where it should go. Right? It should go on that starting material side. So if the reaction temperature is increased to 100 degrees Celsius, well, that is like an increase in delta H, right, which is the same as our starting material, and so that's going to cause our equilibrium to shift to the right or product side. As an example of all of these, we could look at a video demo. And of this video demo, we're going to look at these very colorful cobalt complexes, where here you have cobalt chloride hexahydrate. And when we react that with ethanol, ethanol being CH3CH2OH, we get an exchange of this ligand of ethanol for the actual H2O. So here we have the equilibrium reaction that we're going to take a look at. We get our balancing correct here. We'd have to have a 6 there in front of the ethanol. And so these are all technically aqueous species. So all of them really have an impact on the equilibrium. Just so happens that our cobalt chloride hexahydrate is very pink, and our cobalt hexaethanoate is actually very blue in color. So this kind of gives us a very good visualization of how we can change the equilibrium process. So one way we could force this reaction to go from one side to the other would be by the addition of hydrochloric acid. Now, you might wonder what this has as an impact. Well, hydrochloric acid is a source of H+, and protons, as they're called, H+, react with H2O to form hydronium ion. So this is basically causes the product H2O to decrease in its concentration. So we're causing a decrease in concentration by the addition of this HCl as a result of the addition of acid, and that's a product. We see the 6 H2Os on the product side, and so since we're removing a product, it's causing the equilibrium to shift to the product side. We could also add water to this process, and I know this is kind of a hard one for us to understand because we've been told that H2O is a pure liquid and it's not part of our equilibrium expression, and that's true for almost every single one except for like this particular reaction. Since the water is actually part of the pink cobalt chloride hexahydrate, it actually does have an effect on this particular equilibrium process. That's why I've been putting the H2O as aqueous. But I don't want us to get lost on that topic that pure liquids are not part of equilibrium constants. This one is just for the demo purposes. So we have the addition of H2O, right? That's now causes increase in our product concentration, and so that's why we see the shift to the opposite side of the process. The other thing that we should know about this reaction is that the delta H for this process is positive. So that would be like having our delta H on our starting material side. So if we increase temp, we would see a shift to the right. If we were to decrease temp, we would see a shift back to the left. And so this demo kind of brings, all of these into play. We're going to look at the addition of acid, see how that changes the colors from pink to blue, look at the addition of water, see how we can then push the equilibrium back to the other side by the color change from blue to pink. And then we'll see a temperature effect there as well. Take a look. So here, looking at this cobalt hexahydrate, we have the nice pink color. We're on the starting material side. We're going to add HCl, and that's going to remove the H2O product and drive the reaction to the product side. Remember, the product side would be the blue side, and so we can see that blue evolving as we add a little bit more and a little bit more HCl to the process. And there we go. We're now on the blue side of the equilibrium reaction. We've added that stress of removing product. Now the stress is we're going to add product, and we're going to push it now to the starting material side or the pink side. And we can see that pink color develop as we add more and more of that actual H2O. And to be honest, we can go back and forth, right? We can add HCl and push it to the product side by removing product and turn it blue. We can then add more H2O and add product and push it back to the starting material side. So that's how concentration affects equilibrium. The next demo here is looking at temperature effects. And so there's our cobalt chloride hexahydrate, beautiful pink color. And as everything we learned today with using a U-tube. So here our U-tube separates the liquid so we can heat one side of the tube while keeping the other constant temperature. When we use our Bunsen burner and we heat the side, we'll slowly start to see that pink color turn purple and then blue. Remember, this is an endothermic reaction. So delta H is on the starting material side, and if we're increasing the delta H concentration by increasing temperature, we're now going to push it to the product side, which is going to be the blue side. And we can see it's getting more purple, and then eventually getting blue, while the other side, which hasn't had the temperature change, is remaining in that pink colored state. And that is all of Module 15.